Okay, so time to get started. Now, before we get into the math, I want to call your attention real quick to the lecture schedule. Recall this is on the Sakai site, the section Sakai site, not the course Sakai site, but just the one for my sections. The page over here on the left is called lecture schedule. Do make sure to keep a close eye on this. Whoa, what did I do there? I hit a button. Make sure to keep a close eye on this regarding the homework, regarding exam dates, that kind of thing. So I'm just going to call your attention real quick to homework number 1 here, and note that we've already finished sections 1.6, 1.1, and 1.2 in the book. Notice that those are in the box here for homework number 1. Notice also, though, whatever we finish today, right, this green cell right here, also in the homework 1 box. Rows are dates all the way across this table is the organizing principle. And so anyway, notice that what we do in class today, what we finish in class today, and always a reminder, it's not really just a question of what we finish in this section, but I have to finish it in all the sections because I want to keep all sections in parallel on the homeworks. So at the end of the day, I will fill out what goes in that box. That will complete, whatever that is, that will complete the definition of homework 1. Again, you look at the content syllabus to see the assigned exercises, and it's due on Friday. Right. Okay, so just a reminder about that. Some of y'all have been interested in turning in the homework early, and I applaud the industriousness. But in order to turn in the homework, of course, it has to be done Gradescope. Gradescope requires that we tell it exactly what to expect to be submitted, and I can't tell it what to expect to be submitted until this last entry is filled out. So it is not possible to turn in your homework before we create the Gradescope item. Typically, it'll be on Wednesday, late afternoons, evenings, something along those lines. Surely no later than Thursday, but the plan is for it to be done on the evening of whatever is the last day defining the homework set. Okay. All right. Any questions about the homework logistics there? Everybody's happy? Okay, good. All right. So back into the math. We finished 1.2 last time. We're going to move on to 1.3 about dot products. Y'all have seen dot products before. It's from linear algebra, and I'm mostly going to not talk about dot products because, again, it's all review, and again, we're extremely pressed for time in this course and all that I've said before. So the main thing I'm going to say here is review, and make sure that you remember all that stuff about dot products. There's a bunch of stuff, lots of properties of dot products in the book, and in your old Math 218 book, or 221, depending on what you took. I will comment on a few things, though. So, first of all, and this is just a comment for your kind of reminder. Dot products lead the way. They're the model on which we base the construction of this idea of an inner product. Right? So it's not just, how important are dot products? It's not just what can you do specifically with dot products, but that led the way to all of these extremely powerful things that you can do with inner products. Okay, so that's just a cultural point reminder. I do want to quibble with language a little bit. Our book uses these two words interchangeably, and I think that's unfortunate. Point being that we have two ideas to talk about. Two different, closely related, but different ideas. And we have two words with which to describe them. I think it makes sense to use one word for one concept, the other word for the other concept. Right? So we want to distinguish between ideas when we should use distinct words. So to be clear, first on what the differences are between the ideas, there is a geometric notion in play here. And the geometric notion is the idea of perpendicularity, namely you look at the angle between two directions. Right? If you have two directions, that defines an angle, and perpendicular means that angle is a right angle. Okay. Notice, in order to have perpendicularity then, you need to have two directions. which means that the vectors can't be 0. 0 doesn't point in any direction, or it points in every direction, or something. I don't know. There's some, anyway, it's weird, and you can't define an angle if one of the vectors is 0. Right? Okay, so the perpendicularity, non-zero vectors only. Now, on the other hand, there's this algebraic idea, namely dot product being 0. And you recall that, again, these are very closely related. If you have non-zero vectors, dot product equals 0 means perpendicular. Perpendicular means dot product is 0. It's seemingly the same thing. Again, though, this allows the 0 vectors. Perpendicularity does not. Right? So these are two different ideas. There's a geometric idea, there's an algebraic idea. Yes, they're very closely related, but they are different, and we need to use the right word for the right one. Right? So please do be careful about that. I like to use, and I think the conventional standard is to use perpendicular for the geometric version of this, and orthogonal for the algebraic version of this. Okay. All right. Questions? Everybody buy it? Okay, couple other things I'm going to say about dot products. And again, tough choices, time constraints, and all that. I'm going to go through this stuff pretty quickly because I think this is pretty readable, possibly review. But these are not as challenging as other ideas we're going to face in the course, and so I'm going to choose accordingly on time constraints. This one I feel sure you know already, but if you want a unit vector pointing in the same direction as a given non-zero vector, this handy-dandy formula right here will do it. Neat trick, not hard to believe. Make sure you remember that. Then we're going to go on and define, using that trick, we're going to define something called the component. And you may or may not have seen this before. This is a useful concept. It's useful in the following scenario. Suppose that you have one vector whose role in this circumstance, whatever the circumstance is to define a direction. This is the direction we care about. That's all we care about, and I just don't care at all about stuff that's happening in that direction. The perpendicular direction. I don't care. So easy example: football. Right? If the ball is here, and there's a pass, right, and then the ball is down there. How many yards gain is that in football? Is it that many yards gain? No, of course not. Right? No, it's, how far in this direction did the ball go? In other words, this distance right here is how many yards were gained. So, anyway, this is the idea of a component. And in particular, if you have a direction defined, direction being defined by the vector v, that tells us what kind of a component we want. Next question is, what is the vector whose component we're interested in? That's what we're going to call w, right? And then the component itself, the component of that blue w in the green v direction, the component is that distance. What do you think? Does everybody see the concept? Okay. Right. Okay, so how to compute it? You can, write out triangles and do trig and etc. and that's fine. But there is a clever argument you can make here, and this is worth noting. The component divided by the magnitude of the w vector, if you think about it, that is exactly the cosine of, let's see here, color choices. It's the cosine of that angle, theta. Right? A little simple trig. Just observing the trig of that right triangle, we get to write down this equation, and of course you can move things around, and et cetera, et cetera. And what you end up with, this is a really nice little clever mathematical twist, multiply and divide by magnitude of v, so that conveniently the numerator will become exactly a dot product, and notice the trig disappears. Right? So another way to say that is the trig involved in computing components and the trig involved in computing dot products, same trig. So you can use dot products to compute components. So this is the final resulting ultra cool, simple, handy formula for computing components. Big trick. Everybody see how that worked? Okay. All right. Now, here's a quick rewrite. I think this is lovely, and I encourage this. It looks like we have a dot product divided by a magnitude. Let's say it a little differently, though. What we have here is a unit vector dotted with our original vector W. So this gives us, I think this rolls off the tongue really nicely. Components are dot products with unit vectors. And I really like it. I don't know, this is maybe a personal thing for me, but I like it when stuff just rolls off the tongue beautifully. It's simple, it's succinct. This is a wonderful way to think about components, and it's a wonderful sort of interpretation of dot products. Components are dot products with unit vectors. So, very handy. Everybody happy with that? Okay. All right. Okay, moving along. Here's a very closely related idea. The projection. Not to be confused with the component. But you look at the picture and you think, oh my God, isn't that the same picture? And it's very, very close to the same picture. We still have one vector defining a direction. That's going to define what kind of a projection are we interested in. We still have a vector W of which we want to take a projection in the V direction. It's still kinda, in some sense, this same side of the triangle is going to be our answer. The big difference is that the projection is not the distance there. The projection is the vector. So it's not that side of the triangle. It's the vector defining that side of the triangle. Does everybody see the difference? Okay. Questions? Feel free. Are we doing good? All right. So how to find the formula for this? There's a million different ways you can think about it. I like the following. I like observing that we have a pre-existing formula for the component. This distance, the component, boom, we already know that. We also have a pre-existing formula for the unit vector that points in that direction. And so, boom, there you go. That's the vector. This vector V that we're interested in, I know its direction, I know its magnitude, and vectors are direction times magnitude. So, very handy. I think this, again, very crisp, succinct, easy to remember, in my opinion. Okay, because again, you already know both of these formulas individually. You already know how to compute components with dot products. You already know how to compute unit vectors from dividing by the magnitude. Now, again, this is the formula that I have memorized and that I use in my life. And you're welcome instead, if you prefer to use the book's formula. The book plugs in this formula for that unit vector, which you'll notice does appear twice. And then kind of moves things around, etc. And they end up with instead this other alternative formula. Instead of expressing it in terms of the unit vector, they plug in for the unit vector. And I think they get an uglier formula. I think it's a little harder to remember. I think it's less intuitive. I mean, again, I'm going to make the plug. This is something natural. It's a component. This is something natural. It's the unit vector. By contrast, what is that thing? Right? W.V over V.V. It's weird. It doesn't have a naturally convenient interpretation. So, look, my own preference is for this formula up above. Suit yourself if you like the one below. Yeah. Oh, sorry. I thought I saw it. Everybody's good? Right. Okie dokie. Okay, last thing I'm going to say in this section is just a comment, and again, tough choices, limited time, et cetera, et cetera. There are some ideas in plane geometry kind of arguments that you can make. You can prove some surprisingly weird facts about geometry using vector algebra. And there's a few examples in the book. I think there's at least one homework exercise, and really it's just a matter of taking geometric pictures, and instead of thinking of edges as being edges, think of them as being vectors, right? And that gives you a foot in the door to use this new tool that you didn't have in high school of vector algebra. Excuse me. And that vector algebra allows you to draw some powerful conclusions. So, okay. Alrighty. And again, very readable. Look at the examples from the book. I think that should be sufficient. Okay, cross product. And this is another topic where I'm going to have to refer you to read some of it on your own. And I think most people have seen cross product before, but my experience with Math 219 and previously Math 212 is a lot of students had not seen it, in fact. And so I am going to go through most of this. There are a lot of tricky ideas in talking about cross products and determinants and right-hand order and things like this. So there's also the question of how you prove all of these results. And the book has its choice for how to prove these results. That's great. I have a different order that I like to present the ideas that I think makes the proofs easier, and it makes the proofs more geometrically satisfying. This is personal preference, right? So you're going to notice that the order that I present the ideas and the arguments that I use to support, justify the claims that I'm making are pretty different from what's in the book. So again, your choice. I encourage you to look at both. Again, ideas are all fair game, and so think about all of it. The tough choice aspect of this, though, is that if I go through all the proofs, it takes too much time, and I just don't have the time, and it makes me very sad because these are really cool proofs. So it's very disappointing to me, but I've come around to the painful conclusion I just can't justify enjoying myself as much as I would if I were to do the proofs. So I'm going to give you the results. We're not going to prove them. Oh well. So anyway, I want to start with the idea of a list of vectors. I want to distinguish between a list and a set. A set doesn't have an order. A list has an order. Kind of like a sequence, right? Has an order. Okay. So very importantly, if you have an ordered list of vectors, let's say A comma B. So very importantly then, A is first and B is second. Right? All right. Well, then I want to talk about not the pair. I'm not going to talk about the pair. I want to talk about the list, specifically the order in the list. Something about that listing, something about that choice to have A first and B second is geometrically interesting. And here's the way I like to think about it. When you, in some sense, go from one to the other, A first, B second, of course, that's the list. Notice that sometimes, depending on how the vectors exist in space, sometimes that order naturally would be viewed as counterclockwise. On the other hand, now, same list, A comma B, but if the vectors are pointing in different directions, A first, B second, notice here, clockwise. Right? So, a list of vectors, non-zero, I should have said non-zero. Anyway, a non-zero list of vectors is either clockwise or counterclockwise. And then there is a third possibility, so I guess this is fine. The third possibility is that something weird happened. And take this, for example. Here, they're linearly dependent. The vectors point in the same direction. There's no clockwise or counterclockwise. And likewise, if one of the vectors were zero, you just can't make any sense out of clockwise, counterclockwise. So the third case is linearly dependent, and there's several different versions of it, and it's just it's kind of the annoying. I guess that's always a possibility. Okay, so clockwise and counterclockwise. Is everybody on board? Again, this is not a property of the set of vectors. It's a property of the list, the ordered list of vectors. Alrighty, so these concepts, clockwise and counterclockwise, have some nice properties. I mean, like, really interesting, beautiful properties. So, for one thing, they're mirror images of each other. So what I mean by mirror images is, if I have, for example, hypothetically, let's suppose that AB is a counterclockwise order, as I have it drawn in that picture. If you reflect over some line, like it's a mirror, right? And then you look at, okay, well, what about A prime, B prime? What about the reflection? See, here I have these reflections, A prime, B prime. Notice that is clockwise. So the way we say this casually is counterclockwise and clockwise are mirror images of each other. I think this is pretty believable. We've all looked at clocks in the mirror and gotten confused because the hand's going the wrong way, you know. Okay. Pretty believable. Okay, next. If you trade the position of two of the vectors in your list, well, there are only two vectors in the list. If you switcheroo and put, instead of A comma B, if you instead do B comma A, notice that what had been, for example, A comma B counterclockwise, exact same two vectors, exact same set of vectors. It's still A and B, but now as a list, different order. B first, A second. Even though it's the same vectors, that list is now in the other order. And again, no surprises, well, perfectly obvious, right? You can see the picture. It's no question as to why that happens. All right. Everybody happy? Okay. All right. And then lastly, I think this is a cool one. Rotations don't do anything. So in particular, if you have a list that's counterclockwise, for example, rotate both of those vectors. I'm going to do a rotation here. It looks like I'm rotating this vector around. Oh, well, let me try to be more careful. I'm rotating this around and I'm rotating this by the same amount. A and B both rotating, right? Then the rotated vectors also counterclockwise. And again, geometrically, will of course, right? If you turn your head to the side, clocks still go the same direction. Right? So, no surprises there. Okay. All right. Now, all that stuff about clockwise, counterclockwise is a segue. It allows me to motivate a much harder to sort of wrap your brain around concept called right-handed order and left-handed order. And it's just one step up. It's a three-dimensional version of clockwise, counterclockwise. So again, it's not about a set of vectors, it's about an ordered list of vectors. It's about the order that they're in, specifically, and how to describe that geometrically. How to find, what I'm going to say, two sort of, non-annoying possibilities that are mirror images of each other, where trading position changes the answer, and that are independent of rotations. Is there a version of that in three dimensions? And yeah, absolutely. It's called right-handed, left-handed. So I have to physically demo how this works. The idea of right-handed, left-handed is, now keep in mind, these vectors are in a specific order. A is first. Right? And so the rule for right-handed, left-handed, let's start with right-handed. Index finger of your right hand, thus the name right-handed, pointing in the way that index fingers want to point, right? Parallel to your palm, in other words. Then your middle finger bending the way that middle fingers want to bend. Please don't do hand yoga, I like to call it, right? Just middle fingers bending the way they're supposed to. Index finger remaining parallel to your palm, middle fingers bending the way you're supposed to. You can then orient your hand somehow as needed so that your index finger is pointing in the direction of the first vector, your middle finger is pointing in the direction of the second vector. So, second vector, B, And so in the example that I have over there that I'm coloring on, it would be about like this. Let's see, something about like that, right? And so now then, those two vectors define a plane. Your thumb of your right hand, and again, this is only for your right hand, your thumb, and again, no hand yoga, right? But your thumb points on a well-defined side of that plane, right? And if the third vector is on the same side as your thumb, as it is in this case, first, second, third, it's on the same side of the plane as your thumb, then that is what we call a right-handed list. Everybody see what I'm talking about? So again, it's all about the hand gesture. You gotta make sure you understand the hand gesture. Index finger parallel to the palm, middle finger bent the way it wants to. You can orient your hand around as necessary while maintaining that sign, with your hand, and then look at your thumb. Okay. So you see, as I have it drawn here, that is a right-handed list. Right. And by contrast, and I think you can probably fill in the gaps and speculate for yourself what a left-handed list. This is a left-handed list, and my demo A, B, C. Right? But if you were to try to make this what I have circled now, if you were to try to do that with your right hand, it's going to crash and burn. Because look, so I point my right hand index finger, first vector A. Middle finger B. Now it's tempting to say I can't get my middle finger over to where B is, but I can if I turn my hand like this. And look at that, I can totally get my middle finger in the B direction, but notice now my thumb points down. That's the wrong side of the plane. C points up, my thumb points down, so that is not right-handed. Everybody see what I'm saying? So every tree, vast majority of non-anomalous lists of vectors are either right-handed or left-handed. And then annoyingly, there is the anomalous, annoying, they might all be parallel to the same plane, or one of them might be zero, or two of them might be parallel. Oh, these annoying possibilities, all of which are linearly dependent. So linearly dependent is the way I like to phrase the third case. Okay, everybody good? So again, pretty easy pitches, and I'm just going to point to the pictures. I think this is pretty believable. Right-handed and left-handed are mirror images of each other. If you have a right-handed list and you reflect the vectors through a mirror, the result is a left-handed list. Easy hand proof, right? Okay. Second. And this is a little bit harder to do with your hand, I suppose, but if you have a right-handed list and if you switch the order of two of the vectors, any two of the vectors, then that turns right-handed, turns right-handed into left-handed. Now the weird thing here is we're not talking about different vectors. Here we're talking about different lists, right? So same vectors ABC. ABC is in right-hand order, right? But BAC is in left-hand order because B first, A second, thumb C up third. So it's not in right-hand order. I would fail if I tried to do that right-hand order, but it is in left-hand order. All right. And independent of rotations. And again, I think pretty believable. So, what we have here's ABC. It's in right-hand order. Notice if I take this list and rotate all the vectors in some way, still right-hand order, because after all, if I have a right hand, and if I rotate that right hand, it is still a right hand. Right? So, again, no surprise, highly believable. Okay, so, shocker, we have a three-dimensional analog of clockwise, counterclockwise. It's right hand, left hand. And it's shockingly natural geometrically. Now, there's a fourth property here I want to talk about, and there is no three-dimensional version of this exactly. This is kind of, this first appears when you get to 3 dimensions. and that is that if you cycle the vectors, so cycling means I'm going to take whatever was third and put it second, whatever was second and put it first, and whatever was first, I'm going to put it back to third. So just kind of, it's like you push them and then something falls off and you put it back on the other side, if you will. When you cycle a list, the order doesn't change. So if ABC, for example, is a right-hand order, as it is in this drawing, ABC is right-hand order, so is BCA. Yeah, question?
Will this just be the same as making two swaps? So it just goes from...
Oh, yeah. That's a good observation. Yeah, absolutely. I have a different sort of preferred way to think about it, and that is, it's this argument right here. Let's see if I can do this. Yeah. Boom. Right, cycling is literally this geometric motion right here. Everybody see what I'm doing with my right hand? So if that's ABC, then that's CAB, and I'm not. My wrist is not flexible enough to go the other way. But anyway, you can see that this cycling, right hand to right hand. Okay, yes, absolutely. Okay. Alrighty. So what are we going to do with it? What does this have to do with math? Why do we care about clockwise, counterclockwise? Isn't that mostly about time telling, and what does that have to do with math? They show up powerfully in linear algebra, and so here's a setup that now I hope you've seen this, but again, maybe not. So I'm covering all this just in case you haven't, and a good review for those of you who have. If you start with a list of vectors, and again, it has to be a list. There has to be a well-defined notion of which one is first and which one is second. You can use a list to make a matrix like so. First vector becomes your first column, second vector becomes your second column. Now that's just a definition I'm going to make. A list defines a matrix. Now, thing is, if you have a matrix, that defines a linear transformation. I already knew that. And here's the other thing. If you have a linear transformation, I can ask the very reasonable question, what does that linear transformation do to the unit square? What's the image of the unit square? And then I can point out that, okay, well, I can look at this edge here, the first edge of the unit square. That's just E1. If I put E1 into there, and if I multiply then the matrix times E1, well, I get the first column, namely, I get the first vector in the list. Right, and then likewise for the second column, for the image of the E2, the image of the second edge, if you will, of the unit square. The image of E2 is the second column, let's see here, second column becomes the second edge. And so, neat fact, if you take our reminder, we have a list that makes a matrix, that makes a linear transformation. If you plug in the unit square into that linear transformation, you get exactly the parallelogram that you would have gotten if you took the first vector, made that an edge, and the second vector, and made that an edge, and then use that to define then a parallelogram by linearity. Okay. All right. Now, yeah. Go ahead.
Sorry. What is S?
S is the unit square.
Okay, unit square.
Yeah. I guess I didn't write that down. Yeah, it's just unit square. So 0, 1 on the x-axis and the y-axis. Yeah. Okay. Now, I haven't really done anything yet. Just I've taken a list and then I've created some stuff. Right. So here's the shocking statements that we're going to get from this. One is the determinant of that matrix and the area of this parallelogram are closely related. They're not the same. They're not exactly the same. Determinants are allowed to be negative. Area, on the other hand, is an intrinsically positive concept. Like distance is an intrinsically positive thing. So they're not equal, but they are equal in absolute value. So, really cool fact, the absolute value of the determinant always gives you that area. I consider this to be a shocking result, After all, determinant, if you think about it, flashback to when you defined determinant, it was defined in this very algebraic way. There was no geometric picture particularly. It's the whole, let's see, what is it? A1 B2 minus B1 A2. So purely algebraic, and yet you get as a result a purely geometric concept, namely area. That's weird, right? Does everybody see how? I hope you see how weird that is. Here's the other thing: not only do you get a geometric result, but you get a geometric result that seems like it should have been a lot more work. How normally would I compute this area here? This area, well, I'd drop a perpendicular. And then I'd measure this magnitude. Wait, how do I measure magnitudes? Well, we have a Pythagorean formula. It involves square roots. And then I have to multiply by that distance, also a square root. Where did the square roots go? Right? The formula we have for area doesn't involve any square roots. And furthermore, I kind of glossed over the fact that the way I would find that, perpendicular requires a little bit of trig. Where'd the trig go? How come there's no trig in this point? It's just determinant. 3-function arithmetic. It's very, very weird and shocking, and it's kind of a jaw dropper, in my opinion. Okay, nevertheless, cool, true fact. Next true fact, there's another relationship that, again, sort of algebraic to geometric. Again, about the determinant. Again, of this matrix. If you look at the sign of the determinant. And remember, sign is what you threw away when you took the absolute value. All right, so the plus or the minus of the determinant. That sign of the determinant tells you about the order of the list. If the sign is, so there's 3 cases. I better zoom out so we can fit this all in. If the, as I have it drawn here, if the determinant is positive, then you will get, as I have in the picture here, a counterclockwise list. And now I don't have the picture drawn appropriately, but hypothetically, we could instead have the determinant could be negative, and again, the figure does not represent this. If the determinant though were negative, that would mean that it was a clockwise list, and if the determinant is 0, that means that your list is dependent. So this is a beautiful fact. I mean, determinant tells us a lot of really geometric things. Determinant is telling us about area. It's telling us about order, right? And then a couple other things it's telling us. Let me just remind you, this is there's a matrix, but there's also a linear transformation, and we can ask, what does that linear transformation do to the plane? This is a square 2x2 matrix, so this is a function that takes the plane to the plane, and when you have a linear transformation on the plane, you could ask the question, well, does it just kind of shift things around, or does it maybe smush, right? Or possibly worse, does it take the plane and flip it, reflect it, right? Well, you can persuade yourself kind of thinking through some examples that counterclockwise corresponds to there being no flip, and clockwise corresponds to the plane being flipped, or as I write it here, inverted. So a lot of geometric information contained in determinant. Again, you really can't see it from the definition. A1B2 minus A2B1. A lot of powerful geometric information there. Okay. All right. And then there's a 3-dimensional version of the same thing. And I'm basically going to hardly talk about this one at all because it's the exact same thing. In fact, if you were not to know anything about this, and if you were to see this theorem here, and if I were to say, make a wild speculation on what do you think a 3-dimensional version of this theorem would be, you'd probably write exactly this, and you'd be right. It's really the same thing. The big difference is, of course, now there's 3 vectors. Now you get a 3 by 3 matrix. Well, of course you do. That's a linear transformation from R3 to R3. We would naturally speculate that you would look at the unit cube instead of the unit square. Seems like a reasonable guess, right? The result would not be a parallelogram. It'd be a parallelepiped, which is a weird word. And blah, 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 but we wouldn't get area, you'd get volume. Right? The appropriate to 3 dimensions, that's the appropriate notion of size, analogous to area. Right? And again, the sign tells you the order. And again, order now this time is no longer clockwise, counterclockwise. Now it's right-hand order, left-hand order. So it's exactly analogous result and exactly what you would think it would be. Let me pause on this one. Questions? We doing all right? Okay. So, all right. So, some facts about cross product. Here's the definition of cross product. By the way, an apology. I really like, whenever possible, when I make a definition, I like for the definition to be natural. Like if you think about it, you think about the way you add 2 vectors, right? There's a formula for how to add 2 vectors, and you can make a case that if you view vectors as displacements, then adding vectors is just composing displacements. First you move that direction by that amount, then you move this direction by that amount. Altogether you've displaced by that amount. So it really, physically and geometrically, vector addition is very natural. I like it whenever possible to start with some sort of geometrically or physically natural, believable concept to let that motivate the mathematical definition. That's really hard to do here, so I'm not going to do it. Side note, the book tries to do it. I think it comes off pretty weird. Read, form your own opinion. I think it comes off weird. But anyway, I'm instead then, with apologies, going to just start with an entirely unmotivated definition. And then I'm going to try to persuade you that, yeah, it's got some pretty neat properties and it connects to some existing concepts that we know connect to existing geometric ideas. So ultimately we're going to see that it's natural, but we're going to have to kind of earn it as opposed to starting with it. So, yeah, that's suboptimal. But okay. So, So first observation I'm going to make about this seemingly pulled out of thin air, random, weird formula is that it is what I like to call a symbolic determinant. I can't technically call this a determinant. Technically, a determinant is something you do a matrix. A matrix has entries that are scalars, not vectors. So right off the bat, right, having written this down, even claiming that this is a matrix is kind of bogus. It's not really a thing. However, this is one of these situations where if you ignore the fact that this is kind of nonsense and proceed anyway, then it works out great and you don't get any problems at all and life is good. So that's why I'm going to do this. It's extremely convenient and it in fact does not lead to any problems. So if you were to pretend that this is a matrix, right? And let's take the determinant of this matrix. Okay, well, you'd take that and multiply by the determinant of this, which means the E1 component of this determinant, in other words, the first entry is that value, which is this determinant. And then, second, in taking the determinant, going across the top row, we would have this. In other words, that's going to be telling me what's in the second row. And then I multiply by the determinant of, color change. What I get when I cross out its row and column, so I get the determinant of that. Don't forget the whole plus minus plus thing. And there's that determinant. And that whole plus minus plus thing, there's your minus. Etc. So, yeah, how about that? So it's just a matter of going through one term at a time, and sure enough, ignoring the fact that this is kind of all nonsense, that determinant is what the cross product is. Related note, in my life, I have never memorized that formula. I have always used this as the way to remember the formula for cross product. I just know myself. I know that if I tried to memorize that yellow formula, I'd get it back. At some point, I'd have, A3B2 minus A2B3. It's just so easy to get that backwards. But if you think about it from the point of view of this symbolic determinant, we already have memorized that formula, and so there's nothing new to memorize. Okay. All right. Okay, next observation. Next tricky observation. If you take this cross product, if you dot it with some other vector C, now that's weird. We're taking a dot product of a cross product. But if you do that, not hard to persuade yourself. Again, just go through one term at a time and confirm that it works. This dot product is this literal determinant. And again, it just kind of works. You just kind of go through and, all right, let's take the determinant the old-fashioned way. I've got that times, let's see, let me use better colors. I'll start with that times the determinant of this, which you recognize as, there's the C1, and there's that thing. And so the first term in this determinant is literally the first term in that dot product, and etc. Right? So, sure enough, we end up then with another cool formula, and that is that this oddball construction here is an alternative interpretation of determinant. We call this a triple product. I think for pretty obvious reasons. This is a kind of a product construction that involves three vectors. And it is literally determinant. How we doing? Okay. All right. So, roughly speaking, the reason there's a lot of reasons this is important. The main way that we're going to make use of this now, going forward, is that this formula connects things that I understand with things that I don't understand yet. Right? And so in particular, we already understand determinant. We saw some really powerfully geometric properties of determinant just a few minutes ago. We already understand dot products, hopefully pretty well from previous exposure. So we understand those two aspects of this, and then what I'm actually trying to understand better is cross product. And so this formula is valuable because it involves the thing that I want to understand and connects it to things I already do understand. Foot in the door. Okay. All right. Okay. So now begins a long list of facts about the cross product. Again, I'm not going to prove these. It makes me sad. But they're really cool proofs. The proofs are in the notes. I encourage you to look at them. Give them a read. They're mysteriously convenient. And so again, I think very cool, but I'm not going to talk about them here. I just want to make sure that you know these facts. When you take a cross product, the result is always orthogonal to both of the input vectors A and B. Cross products are always orthogonal to both inputs. And, super duper quick, you can prove orthogonality by taking a dot product and confirming you get 0, or you can make this really neat argument down here that I think is wonderful, and again, I don't have time, but take a look. I think you'll like it. Okay, next. Triple products cycle. So A dot B cross C is equal to P dot C cross A, etc. And this one really doesn't seem like it ought to be true because A here, not part of the cross product, but mysteriously here, A is part of the cross product. These seem like they're totally different. How could these be the same? right? But the answer is, again, keeping in mind that triple products are just determinants. When we cycle that list, we're basically just cycling the vectors in a determinant, and we know all sorts of stuff about determinants from linear algebra, that when you switch rows, columns, whatever, we know exactly what happens. And so, again, different ways to think about it. But again, there's a geometric point of view. Give it a look. I think it's very satisfying. But anyway, make sure to know this fact. And then let's see. Oh, and that works out kind of perfectly. I've run out of time. We'll draw the line right there and pick up here on Friday. See y'all on Friday. And again, we'll have the homework assignment defined and posted on Gradescope, hopefully by the end of today. If not, then early on Thursday.
Thank you.
Yep.